But what we're going to do now is listen to the second presentation by Rob van Dorp from Allnamics in the Netherlands, who's going to talk about CPT testing. Rob, floor is all yours.
Okay. Good morning, everybody. For me, it's starting to be evening. I've had a long day in the field, and well, I'm happy to present this webinar. I'm going to talk about not load testing. I'm going to talk about what can you do before you start load testing, and that's soil investigation, and more in particular, cone penetration testing. Does it work? Yeah, I have the controls. So I'm gonna do a short introduction on cone penetration testing. I think and I hope that most of you already are familiar with it. I'm gonna tell a little about design and piling practice in the Netherlands using the cone penetration test. Then I'm gonna talk about a case study showing the importance of good soil investigation. And finally, we'll reach the conclusions and hopefully have some time for question and answers, and otherwise later on. There we go. Before we start, codes are different, of course, in various countries, also in the Netherlands and USA. So don't pay too much attention to the numbers and factors, but look at the approach in general. Is it working? Yep. The cone penetration test is not new at all. It's been around for a while. It started in the early 1930s by mechanically pushing a rod into the ground and measuring resistance. And there's been a lot of development. Nowadays, we have electronic cones measuring cone resistance and frictions, and we have trucks with tracks that can do that trick almost everywhere, and also are very productive. 15 to 20 CPTs in a day is not a problem whatsoever. Typical CPT results, or most important, are a continuous reading of cone resistance. This is pretty different compared to SPT, for instance, where you have readings on intervals. We also have a continuous record of unit friction, which you don't have at all for standard penetration test. And the product of both is the friction ratio. Well, not the product, the quotient of both. And the friction ratio has proven to be very helpful for determining what cell type are we dealing with. So Mr. Robertson, your fellow countryman, has written a lot about it, but from the friction ratio, we can tell this is sand, this is peat, this is clay. Pretty informative. So without doing a borehole, you can already tell a lot about not about the density and the resistance of the soil, also about the stratification and the soil profile, which is very useful. And now if we start the piling, we have cone resistance is a direct measuring of soil strength and soil density, and therefore a reliable parameter for calculating pile bearing capacity. And the only thing we really need to do is translate the small size of the conus to the large size of a pile, and of course installation effects. And based on that, the common practice in Dutch piling using CPT is that a designer is allowed to design the piles based on CPT only. There's no requirement for load test, but there is a requirement for good quality control during installation, like low strain dynamic testing, proper piling records. You've seen in the previous presentation, also with drilled piles, there's a lot you can monitor during installation. But load test to confirm capacity using this calculation method are not required. But of course, they are always allowed if you want to go further than that, and if you think you are smarter than that. Yeah, so engineers can really depend on this direct method without requirements for load testing. Well, and this is based on over 70 years of experience. for many projects. As a matter of fact, almost all of them. And the design method or the calculation method has been validated by load test pretty regular and still is. The calculation method was invented by Mr. Koppian, and he defines three major areas governing or influencing the bearing capacity. There is area number 1, which is about 0.724 times the diameter below the pile toe. There's area number 2, also from that area, and area number 3 above the pile toe. So the penetration into the bearing stratum has an effect, and everybody knows that. Well, if you're interested, you can look up Mr. Koppian and Google him, and perhaps you can find something. But the main trick is the conversion of the measured resistance from a cone penetration test to the larger diameter of a pile. And especially right here, these stretches above the pile and below the pile, they are different for larger pile size, of course. So here we have these three areas again. And what's the trick? Portion number 1 is the average maximum value with a cap. Portion number 2 is the average minimum value. And portion number 3 is also the minimum value in this area. And here are their contribution to the maximum. As you can see, 50% of bearing capacity is defined by the layers above the sole pile toe, and the other 50% by the layers below the pile toe. If we zoom in a little further, the total resistance for pile, I don't need to explain that. There's some base resistance, there is a shaft friction, and depending on cell type, we need to correct for negative skin friction that will develop later on if we have soft compressive layers on top. And so the effective capacity, there we have it, is base resistance, shaft resistance minus negative skin friction. This base resistance is calculated Pmax. I've shown 2 slides before with the calculation method of Koppian. The cross section of the pile, and there's a couple of factors accounting for pile shape, installation method you'll see later on. The shaft friction is in fact the average friction over the friction length multiplied by the circumference and the friction length. And again, we have a factor accounting for the installation method and the sole type. The negative skin fraction is a pretty complicated formula, but is more or less 25% of the effective vertical stress. So you might be dizzy a little with all the factors. Well, I'm not going to rehearse them, but luckily we have a code that it's in Dutch, but it specifies the pile type, the subtypes, the method of installation, and there it defines factors for the pile toe, the skin friction in compression, pile toe factor, skin friction in compression, skin friction in tension. So here we have these applicable factors. And if you have a CPT, that makes the calculation pretty much straightforward. The designer can even make a prediction of the load settlement curve. That's also based on a lot of experience and back analysis of load tests. Here we have it. There are 2 separate curves. There is one for the development of toe resistance. There's another for the development of shaft friction. And these are percentages of the maximum. Here we have for the toe resistance a percentage of the effective diameter, And for shaft friction, we have an absolute value of the substance in millimeters. So if the designer has calculated the ultimate capacity, there we go with the curves again. He can also calculate the curves for the development of toe resistance and shaft friction. You see two on both sides, that's ultimate limit state and serviceability limit states. And the red line in between, in this case, that represents a load of 2000 kilonewtons, 200 that's 200 tons. And just where it fits between the lines, that's the settlement where you can read. So that's 18 millimeters. And so there you also have a nice estimation of load settlement curve. But of course, if you start load testing, that prevails the result. It's always, you can trust it better, or it's more accurate. Now we move on to the case study that I wish to discuss, because it's not about the calculation method. The calculation method hinges a lot on the CPT results, or more better to say the soil profile, and there can be a lot of variation in soil profile and density, even in small areas. So there's a small housing project, 4 or 5 stories high, no basement, pretty simple, and the footprint is not very big, 110 by 65 feet. It's located in the Netherlands, which is on the other side of the Atlantic Ocean. In case you didn't know, here we have the map of the Netherlands. And right here in the west, in the red circle, that's where Hoofddorp is. And if we zoom in a little, there we have Hoofddorp again. And for your information, Schiphol Airport is really close, and the capital of Amsterdam is really close as well. This is about 5 to 10 kilometers, and to Amsterdam, that's less than 15. So you could go there by bike. Before 1815, the location, here we have Amsterdam again, used to be in a lake. And well, your Mr. Trump is trying to drain the swamp. The Dutch have drained this Haarlemmermeer area with steam engine pumps. Still the biggest steam engine in the world, I was told. If you want to learn more about the pumping station, there were 3 of them, but this one, Krukius, is still operational today, although as a museum, not for keeping dry feet at Schiphol Airport. Back to the project. It started off with some indicative soil investigation campaign. Only 2 CPTs, 200 feet apart, which is not very close, but also not very strange, especially for a first impression and basic design. Number 1, we have this CPT. What you can see, there are some weaker layers, a mixture of sand and clay at the top. You can see the friction ratio as well, governing around here. And from here, from 21 minus NAP, the ground level is 5 meters below. It's a drained area, so it's well below sea level. But here we have the sand, which is a regular bearing stratum, and this is more or less what we know from this area. But now we have CPT number 2, and right to this point, 14 meters, they look pretty similar, but from there on, they are very different. And that calls for extra soil investigation, because you want to know which profile is where, so you can adjust your design. So there was a second campaign, and 22 CPTs were added to the original. Still a small footprint. This is a day work for a CPT truck, more or less. But you can see there's quite a lot now, and the grid already looks pretty dense. And if the red line is a profile that I can show you, but it wasn't very helpful. All the lines here, they more or less represent the same layers, and you can see there's a lot of variation, especially if you take into account this green line represents 5 meters. And so from here to here, something like the Bering Stratum, it's 5 to 10 meters deeper. And if you don't have that information and just start piling, well, you can easily imagine that things might go wrong. And well, these areas here, probably like this, but pretty much unknown. So it was decided to launch a third campaign. Again, 22 CPTs, which is a coincidence, might have been 20, might have been 24, but at least no error from my side. And here we have the same profile again, and the solid lines, they were the CPTs that we already had, and the dashed lines, they represent the extra CPTs. And right here in this area, you can see that there's happening quite a lot. Still large differences, over 5 meters in Bering Stratum, and as a matter of fact, Bering Stratum more or less missing. So still a lot of work to do for the designer choosing pile length and toe levels. But in general, you could identify a couple of areas with typical soil profiles. So this was area A. There was an area B, which is pretty wild. And then we have area C, where it becomes a bit more quiet, in a relative sense. And in top view, in the meanwhile, we have 46 CPT on a stamp, as a matter of fact. Profile A was located in this area. Profile B was more or less located in that area. And profile C was in the remaining area. Still pretty close to each other, but because of the large differences, these different soil profiles, they require different solutions for the foundation, or at least for the toe level. So if we take a closer look, typical for profile A, we have these weak layers from the ground level to here. And right here we can see a pretty clear Bering Stratum, also with the friction ratio of 1. Profile C is more or less the same, but with the Bering Stratum at a deeper level. And profile B, which is a small area, but it's difficult. It has some harder lenses, but no clear Bering Stratum. And well, I can tell you the real CPTs, they go a little deeper than that, but these weak layers, they continue pretty far. So for toe levels, the choice was either here or there, but in both cases, low capacity you could expect, and also compressive layers below the pile toe. So that's going to be translated to a low stiffness of the pile. Yeah, so this is what I just said. No clear Bering Stratum here in profile B, and compressive layers below the possible pile toe level. But you cannot say, well, let's not make this building. We need to make a foundation somehow. And again, if you look at the profiles right here, I've just discussed them. What was chosen? Profile A, a toe level at NAP minus 28 to 32, so that's 23 to 27 meters below ground level. I have it in feet right here for your information, but that's pretty straightforward. Sloping down easily, gradually from here to here. So the 28 meters, the shortest piles are here and the longer piles are there. If we go to section C, it's more or less the same, only with a different pile toe level. The difficult part was section B. And it was decided to put the pile toe level at, well, in between, and accept the fact that we will have piles of the same type with low bearing capacity and lower stiffness, and compensate for that by adding extra piles under the foundation slab in that area, so the total capacity becomes what the designer needed for his construction, and also adjust or strengthen the foundation slab itself to be able to distribute the loads from B to A or C, so make up for the lower stiffness and lower capacity of the piles. So that was the solution around here. And if that was translated to a piling plan, there were, well, a couple of sections. So the red section here, that was profile A. We have a small green section, still so profile A, but slightly deeper. And then we have the blue section, which is sole profile A and B together, with all the piles at the same depth. And there's the purple section, which is sole profile C, with the piles at a certain depth. But as you can see, sole profile B was right here in this area, where we have 2 piles per foundation beam. And, well, there's always a lot to discuss about proving more capacity and saving money. But what if we had started to design the pile foundation on these 2 CPTs we started with only, or make trial piles? So the traditional approach might have been only these 2 CPTs at pretty large spacings, and perhaps we could have made a trial pile somewhere here and do a test and use it for the design. But we already know that these 2 locations have different sole profiles, so they do not represent the whole footprint of the building. And it's even a bit worse, because the CPTs that we started with, so number 1 is more or less sole profile A, but the top of the bearing stratum is higher. So if we had designed based on this CPT, it would have gone wrong for A, B, and C, because we might have missed, or too high, for the bearing stratum. The second CPT, number 2, well, resembles profile C, although no clear bearing stratum. So that would have been on the conservative side. But let's face it, if we had based the design on profile on location 1, most piles would have been too short, and that might have resulted in a failure of the foundation. Profile B would have been missed anyway at a very bad location where the bearing stratum is missing and the low stiffness. So that would have caused a failure of foundation as well, perhaps. Did we use CPT number 2 as a basis for the design? We still would have missed profile B, but for profiles A and C, it would have worked, but we would have over-designed the foundations, and in case of driven piles, that might have resulted in other problems with pile installation, and certainly in longer installation times. And as you learned from the previous presentation, that's money too. Yep, so now I'm on to my conclusions. It's good to know that a good foundation requires a proper soil investigation data, a proper design, a proper execution, proper monitoring during execution and after execution. And lack of any of these components may result in failures or damages, or in over-designed foundations. So never ever try to save cost on soil investigation, because it will pay off. And a good soil investigation means detecting variations of soil properties over the project site, much more than making a good calculation of pile capacity based on a limited number of soil investigation points. And so you really need to lower the spacing between your investigation points. That's much more important for a safe design than testing a pile or designing a pile with an overall safety factor that's pretty high, because you still miss out on the weak spots. And cone penetration testing is very suitable for this, because these extra CPTs, they can be made within a day, well, depending on conditions, of course, but on a regular basis, yes, in a standard field. Also, the mobilization time is short, and the cost per CPT is also not that much. So, as a final conclusion, well, Da Vinci already found out unwillingly, but more soil investigation helps optimizing design, and therefore can save a lot of money, but it can prevent a lot, and that's even more money always. And it can easily be achieved with cone penetration testing. And that's it. Thank you for your attention.